drawing up our trig functions then, but now with radians. Again, it's pretty much the same idea, it's just we change what we label the axis. So if I wanted to draw the sine curve, we know sine goes in between -1 and 1. I mark in the key points, so those boundary values. So now instead of every 90 degrees, I'm marking off every pi on 2, but being lazy, I'm just writing the pi's in there. We know the sine curve starts at the origin, it then goes up to 1 and then repeats that pattern and goes down and up and down and up and over in the negatives as well. And we draw in our sine curve, and there it is. Domain, or real x, there's no gaps. Range, as I said, goes between -1 and 1. It is an odd function, we can see that because of the symmetry of our curve there. Therefore, the sine of negative x is equal to the negative of sine of x. That could be useful in some of those problems that we try and solve with relationships. Now with our trig curves, we have these things. We'd like to know about the period. Remember, period is just when something starts repeating. We've got to be careful though, because it looks like pi and 2 pi, it's repeating because it's both at 0, but it's got to be going in the same direction as well. It's the whole thing's repeating. So it takes a whole 2 pi until it repeats. So the period for this one is 2 pi. Amplitude, well, it's just how high up or how far down it goes. So it's 1. Cosine curve then, let's do the same sort of thing. It also goes between -1 and 1, as we know. We mark off all our boundary values there, but our cosine curve doesn't start at the origin, it starts up here at 1, then comes down to the origin, and again that pattern, up and down, up and down. And we have our cosine curve, which looks very similar to the last one. Domain is still all real x, range in between -1 and 1, yep, exactly the same as the last one, but this is an even function. We've got the reflection symmetry. So the property we could use is the cosine of negative x is equal to the cosine of x. Its period is also 2 pi, amplitude is also 1, and that is because they are complementary ratios. We know the cosine of x is equal to the sine of pi on 2 minus x. So I could have actually created this from the sine graph, because I said, well look, it's negative x, so function negative x, we reflect the curve in the y-axis, but then we've also got a horizontal shift happening of pi on 2, and we get the cosine graph. Let's look at the tan one. So again, well, I don't mark in amplitude for this one, of course, because tan goes all the way up to infinity and down to negative infinity, but we'll still mark the boundaries values. It starts at 0, then we have a vertical asymptote, and that pattern keeps repeating. So 0, then asymptote, 0, then asymptote, and so on. We bend towards asymptotes. So there's our section. It should go through at 45 degrees. So our tan curve, our basic tan curve, comes through at 45 degrees. And it repeats in all of those sections. Domain then, for this one, well, it's all real x, but we've got all of these asymptotes. So the easiest way of saying that is just to name one of them. Makes sense to do the first one, pi on 2, and then you say, well, this keeps repeating every pi. So plus pi k, where k's some integer. The range, everything, all real y. It also has rotational symmetry, odd function, which means, again, we could use the fact that tan of negative x is equal to the negative of tan of x. The period for this one, though, is only pi, not 2 pi. It takes pi to repeat. Okay, let's do one of our reciprocals. Cosecant. Cosecant is the reciprocal of sine. So I'll just draw in a construction dotted there. It's not actually part of the final curve, it's just what I'm going to use. Basic curve sine on x, the reciprocal graph. So what did we do for reciprocals? We said, look, all of these x-intercepts will become asymptotes. I know that. I also know that 1, well, when I turn 1 upside down, I get 1. So all those points will remain, but anything that's less than 1 will become bigger than 1. Also, we know anything that's increasing becomes decreasing and things like that. We end up with all these U shapes. They're not parabolas, but they're just U shapes in each of those sections. All right, that'll do it. 11J.